Chapter 6, Momentum. This lecture will help you understand the law of conservation of momentum, collisions in one dimension, and collisions of equal masses in two dimensions. In every case, the momentum of a system cannot change unless it is acted on by external forces. A system will have the same momentum both before and after any interaction occurs. When the momentum does not change, we say it is conserved. Symbolically, we write the sum of the momenta of all objects is equal to 0. A 75 kilogram man and a 35 kilogram boy push off on each other on frictionless ice. The boy moves off at 0.40 meters per second to the left. In what direction and with what speed does the man move? Conservation of momentum says that the sum of the momenta of all objects is 0. There are two objects, the man and the boy. Since momentum is mass times velocity, we can write the momentum of the boy plus the momentum of the man. Substituting the known values gives the velocity of the man as minus 0.19 meters per second. The minus sign indicates the man's direction of motion is opposite the direction of the boy's motion. What force is required to slow a 1,450 kilogram car traveling at 115 kilometers per hour to 45.0 kilometers per hour within 3.00 seconds? And how far does the car travel during this deceleration? We write down everything we know and convert to the appropriate units. The basic equation is the impulse equation, which we rewrite as the working equation by dividing by the time interval. Substituting the known values gives a force of minus 9,380 newtons. The minus sign indicates the force is opposite the direction of motion. The basic equation and the working equation are the same, one of the kinematic equations. Substituting the known values gives 66.6 meters of travel. The law of conservation of momentum. In the absence of an external force, the momentum of a system remains unchanged. In the equation, the total momentum before is equal to the total momentum after. When objects collide, in the absence of external forces, net momentum before the collision and after the collision are equal. There are two types of collisions that we will explore: elastic and inelastic collisions. We now want to look at collisions in one direction. In the figure at top, the ball on the left, M1, is moving to the right with velocity V01 and collides with the stationary ball, M2. After the collision, bottom figure, M1 moves to the left with velocity Vf1 and M2 moves to the right with velocity Vf2. What can we say about the two velocities? Conservation of momentum tells us that the momentum before the interaction must be equal to the momentum after the interaction. The momentum before is the momentum of each object, seen on the left side of the equation. The momentum after is the momentum on the right. Since the initial velocity of m2 is 0, the equation simplifies to m1 times the initial velocity is equal to m1 times its final velocity plus m2 times its final velocity. When objects collide, the collisions can be elastic collisions or inelastic collisions. An elastic collision is defined as the collision whereupon objects collide without permanent deformation or the generation of heat. In other words, the elastic balls bounce. Consider the interactions of two identical balls, one green and one yellow. In figure A, the moving green ball hits a yellow ball, initially at rest. the green ball comes to rest, and the yellow ball moves away with velocity equal to the initial velocity of the green ball. In figure B, the green ball and the yellow ball approach each other with the same velocity and collide. After the collision, the two balls move away from each other, but with the same speed, but opposite direction. In figure C, the green ball and yellow ball are moving in the same direction, but the green ball is moving faster, overtakes, and then collides with the yellow ball. After the collision, the yellow ball moves away from the green ball at the speed at which the green ball was approaching. The green ball is moving at a slower velocity. In figures A through C, momentum is conserved in all cases. Momentum is simply transferred from one ball to the other. You may have seen this little device. It is called Newton's cradle. It demonstrates the conservation of momentum. The conservation of momentum can be used to find the resultant velocities for two colliding, perfectly elastic objects. When the objects weigh the same, the solution is very simple. The moving object stops relative to the stationary one, and the stationary one picks up all the other's initial velocity. This assumes perfectly elastic objects, so we do not need to account for heat and sound energy losses. On the right is Newton's cradle for 3 balls swing in a 5-ball system. The center ball swings without any apparent interruption. The total mass of the swinging objects is equal in both cases. 3 balls come in and 3 balls move out. We will analyze Newton's cradle in more detail when we discuss energy. One ball of mass 0.600 kilograms, traveling 9.00 meters per second to the right, collides with the second ball of mass 0.300 kilograms, traveling 8.00 meters to the left. After the collision, the heavier ball is traveling 2.33 meters per second to the left. What is the velocity of the lighter ball after the collision? We write down what we know, the masses of both objects, the initial velocities of both objects, and the final velocity of the heavier ball. The final velocity of the lighter ball is not known. Since the momentum before must be equal to the momentum after the interaction, we sum the momentum before the interaction and after the interaction. The only unknown is the final velocity of the lighter ball. Solving for this gives us 14.7 meters per second to 3 significant figures. Since the velocity is positive and positive is to the right, the velocity is 14.7 meters per second to the right. An inelastic collision is defined as a collision whereupon colliding objects become tangled or coupled together, generating heat. Inelastic collisions are often sticky. In the figure, 2 identical freight cars collide. The combined freight cars move off with half the velocity. The 3 figures show the types of collisions. The top is an elastic collision. In a perfectly elastic collision, a drop ball returns to exactly its same height. The second is an inelastic collision. The ball deforms when it hits the ground and loses energy and does not return to the same height. The third is a completely inelastic collision. The ball does not bounce at all. Freight car A is moving toward identical freight car B that is at rest. When they collide, both freight cars couple together. Compared with the initial speed of freight car A, the speed of the coupled freight cars is A, the same, B, half, C, twice, or D, none of the above. Answer is B, half. After the collision, the mass of the moving freight cars has doubled. Can you see that their speed is half the initial velocity of freight car A? A 1.75 times 10 to the 4 kilogram railroad car traveling at 8.00 meters per second to the east collides and couples with a stout 2.25 times 10 to the 4 kilogram railroad car. What is the velocity of the joined railroad cars after the collision? Well, we know the mass of both railroad cars and their initial velocities. Since the cars are coupled together, the final velocity of the two cars must be the same. The momentum before is the sum of the individual momentum of each car. The final momentum is the sum of the masses of both railroad cars times the final velocity. Solving for the final velocity gives 3.50 meters per second. Since we are asked for a velocity, we must specify a direction. Since the velocity found is positive and positive is east, the velocity is 3.50 meters per second east. When two objects of the same mass collide, they move off at an angle of 90 degrees. That is to say, the angle of separation after the collision is 90 degrees. A 2 kilogram mass, m sub a, is moving in an easterly direction at a velocity of 5.00 meters per second. It crashes into a 2.00 kilogram stationary mass, m sub b. Mass m sub a is deflected 30 degrees south of the original path, and mass m sub b is directed 90 degrees away from m sub a. What is the initial momentum of m sub a before the collision? What is the momentum of m sub a after the collision? What is the momentum of m sub b after the collision? What is the velocity of m sub a after the collision? And what is the velocity of m sub b after the collision? First, draw a picture. The two objects are the same mass, so they move off at an angle of 90 degrees from each other. Object A is moving toward the at-rest object B. After the collision, object B moves upward at an angle of theta to the horizontal. Object A moves downward at an angle of 90 degrees minus theta below the horizontal. The two angles sum to 90 degrees. We can draw a vector diagram. Conservation momentum means the momentum before equals the momentum after. We know the mass of each object, both 2.00 kilograms, and we use m for both masses. Mass A is moving 5.00 meters per second to the east, and mass B is stationary. We are given the angle of mass B to the horizontal after the collision is 60 degrees. Therefore, the angle of mass B to the horizontal after the collision must be 30 degrees. By using the definition of momentum, the magnitude of the momentum of mass A is 10.0 kilograms meters per second. Looking at the right triangle, we may use our understanding of right triangles to solve this problem. The hypotenuse is the side opposite the 90-degree angle, and it is equal to the initial momentum of mass A. The final momentum of mass A is the side adjacent to the 60-degree angle, and is equal to the initial momentum of mass A, the hypotenuse, times the cosine of 60 degrees. The final momentum of mass A is therefore 5.00 kilograms per meter per second. To solve for the final momentum of mass B, we again use the properties of the right triangle. The hypotenuse is the initial momentum of mass A. The final momentum of mass B is the adjacent side to the 30-degree angle. The final momentum of mass B is equal to the initial momentum of mass A, the hypotenuse, times the cosine of 30 degrees. The final momentum of mass B is 8.66 kilograms meters per second. Since the momentum is the mass times the velocity, Dividing by the mass gives the final velocity of mass A as 2.50 meters per second. Since the momentum is the mass times the velocity, dividing by the mass gives the final velocity of mass B as 4.33 meters per second. The important formula for this chapter are the definition of momentum, P equal m times v, the conservation of momentum, momentum before an interaction is equal to the momentum after the interaction, and the impulse momentum theorem, force times the time interval, or the contact time, equals the change in momentum. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. Problem 1. Calculate the impulse of a cart when an average force of 11 newtons is exerted on it for 2.6 seconds. Pause the video to work on the problem. Did you get 29 Newton seconds? Which of either has greater momentum? A 1 kilogram ball moving at 2 meters per second or a 2 kilogram ball moving at 1 meter per second? Pause the video to work on the problem. Did you say they are the same and equal to 2 kilogram meters per second? An automobile accident investigator needs to determine the initial westerly velocity of a Jeep mass 1,720 kilograms that may have been speeding before colliding head-on with a Volkswagen of mass 1,510 kilograms that was moving with a velocity of 75.7 kilometers per hour east. The speed limit on the road is 90 kilometers per hour. After the collision, the Jeep and the Volkswagen stuck together and continued to travel with a velocity of 15.5 kilometers per hour west. Find the initial westerly velocity of the Jeep and was the Jeep speeding? Pause the video to work on the problem. We must use conservation momentum to solve the problem. We know the mass of the Jeep, 1,720 kilograms, the mass of the VW, 1,510 kilograms, the initial velocity of the VW, 75.5 kilometers per hour east, and the combined final velocity of the Jeep VW system, 15.5 kilometers per hour west. We do not know the initial speed of the Jeep, but we know it was traveling west. Our equation is mass of the VW times the velocity of the VW plus the mass of the Jeep times the velocity of the Jeep equals the mass of the Jeep and the VW combined times their combined final velocity. We will assign east positive and west negative. Substitute what we know and solve for the missing value, v Jeep. We find that the velocity of the Jeep initially was minus 95.4 kilometers per hour. The minus sign indicates the Jeep was traveling in the westerly direction, as stated. And yes, the Jeep was speeding. Your assignments are to read Chapter 6 in the textbook and watch the videos on Blackboard. Your homework assignments are due February 23rd.